Hi, my name is Søren. I'm a product manager at the Danish Technological Institute. In this video, we will look at quality control for additive manufacturing. The agenda for this video is about how to approach quality control for additive manufactured parts. Furthermore, the video will look into typical defects and deviations for additive manufactured technologies and also their related test methods. And finally, we will take a look at the standardization activities for additive manufacturing. First, we will look at the need for quality. As for any other materials or production technology, quality control in additive manufacturing is needed and necessary in order to ensure desired material properties and, for instance, avoid claims and failures. When we produce components, we usually want them to be consistent and according to requirement, and that also counts for additive manufactured components. Let's start by looking at why quality control for additive manufacturing is needed. Additive manufacturing, or AM short, has been on transitioning from prototyping to production technology, which also means that quality control and product specifications has been increasingly important. In AM, we have to deal with variations from one machine supplier to another, and also from one machine to another, and from one production batch to another, within one production batch, and so on. And all those potential variations may require quality control and proper product specifications. So how do we deal with quality control in AM? Quality control of AM parts can be difficult since we are not dealing with standard geometries and shapes like plates and bars and etc. Typical AM parts consist of complex design, organic design features and structures, inner geometries as complex channels, and so on. So, first of all, the fundamentals should be in place. That means that there should be facility and standard operating procedures describing how it's being manufactured specifically to the facility, regardless of what is being made. On top of that, part qualification and product specification should be specified, defining the specific quality requirement for the part. As for any other production technology, the level of quality control is individual and should be taken into account. For instance, if we look at the requirement for a simple keychain, no major risk associated with failure, maybe limit strength requirement, maybe requirement for surface finish and post-processing, but that's it. And if we compare that with, for instance, a combustion chamber for a rocket, we might have high financial and personal safety risk associated with failure. You may have high strength requirements to withstand large thermal loads and vibrations, maybe fine tolerance requirements in connection with coupling of other components, and also maybe requirements for surface finish in connection with flow properties. So, we have to deal with different kinds of components and application level. Quality control is often expensive and time-consuming. The more properties and tolerances specified, the more expensive the 3D printed parts will be. And it's very important to avoid over-testing also. The quality control should focus on specific and individual application requirements. In general, there are several ways to obtain the desired level of quality. However, a common thing is that the initial design and specification phase should be used to define the necessary processing parameters. That could, for instance, be laser power, scan speed, layer thickness, and so on, and that is for sure technology dependent. The necessary process parameters are often determined with an initial qualification build demonstrating achievement of the desired final part quality. Then you should look at the desired or needed quality approach, what requirements should be inspected, which test method should be used, and the needed inspection rate. Example of different AM quality control approach could be, for instance, quality control during the manufacturing phase, where we can do in-process monitoring and sensor data. We can do inspection of our incoming and raw material. And when we have the final part, we can also do quality control. We can, for instance, do validation of our final part properties by use of test samples, artifacts, when the builds are done. Furthermore, we can do validation of our final parts by use of destructive and non-destructive methods when the build is finished. Depending on the application of the 3D printed part, a combination of both quality control during and after manufacturing can be necessary. Quality control of our raw materials can be done in several ways. First, we can do incoming quality control of our raw materials by looking at or inspect our material certificates. We can also do characterization of our raw materials. That could, for instance, be size, distribution, composition, and so on, depending on the production technology. You could also do quality control of specific build material by taking a small sample from each build and then store it for later on. The outcome is desired quality of our raw material before manufacturing and also traceability of build-specific raw material in case of any deviations. When looking at monitoring of in-process parameters, you could, for instance, look at build chamber temperature, gas flow speed, the oxygen level inside the chamber, and also melt pool data and platform temperature, and so on. And for sure, all those parameters are technology dependent. And the outcome of in-processing monitoring data could, for instance, be a quality control report based on sensor data. Acceptance criteria could be based on predictions from a digital twin or by experience. The pros of this monitoring is easy and fast approval of build. It is cost effective, and also we get non-destructive evaluation of our parts. The downside is that you only indirectly get the final part properties. As mentioned, test samples and artifacts can be beneficial when we do quality control of AM parts. For instance, tensile samples can be added to our build platform in order to achieve mechanical properties of our build. The tensile samples are typically positioned strategically on the build platform to represent the entire build. Furthermore, standardized artifacts can be added to the build platform in order to achieve or measure geometric tolerances and also to validate linear distances. The outcome of test samples and artifacts could be certificate and test reports, including material properties, and acceptance criteria is typically according to customer or standard specification. The pros is true material properties and also non-destructive evaluation of our final parts. The downside is that destructive testing is time-consuming. Furthermore, potential deviation and defects in our final parts may not be revealed from our test samples. Another step could be to test our final parts, and that could include all kinds of different test methods, for instance corrosion test, mechanical test, non-destructive test, and so on. Basically, it's dependent on the application, but it's relevant for all AM technologies. Outcome of such test could be test report including final part behavior and properties. Some of the pros is true final part properties, and it's very ideal for initial qualification of parts and functional testing. The downside of test of final parts is that it's often very time-consuming and expensive, and also it can be destructive if we do mechanical testing. Traceability is also a part of the quality control, and it's important through the entire manufacturing chain, and that covers raw material, machine parameters, sensor data, measuring data from test sample and final parts. Let's say in case of a failed component, the manufacturing chain can be investigated and root cause can be identified. Next up, let's look at typical defects and deviations in additive manufacturing. The typical defects and deviations can be divided into 4 general categories. That is surface quality, dimension and geometry, internal structure, and mechanical properties. Of course, all those defects and deviations depend on the specific AM technology and material that are used. If we look at the surface quality, the as-built surface roughness can be high for some AM technologies. Also, the as-built surface roughness can depend on the print direction, and for most AM technologies and applications, post-processing is required to obtain the desired surface quality. Typical validation methods of the surface quality are contact profilometer stylus and non-contact profilometers. If we look at dimension and geometry, most AM technologies involves thermal processes to some extent. This might lead to distortion, shrinkage, or dimensional deviation from the CAD model. Typical validation methods for the dimension and geometry could be by use of simple vernier calipers, or if more precision is needed, coordinate measuring machines can be used. Depending on the AM technology, different internal defects or deviations might appear. Some of the typical issues you see in additive manufacturing relates to porosities and anisotropy. Porosities are material defects that may look different and have different effects on the material properties. In general, porosities has a negative effect on mechanical properties and the corrosion resistance. Porosities may, for instance, appear as lack of fusion, where they act as a notch or a stress concentration, which might reduce the fatigue properties. They could also appear as, for instance, gas entrapments, and those are less critical in relation to fatigue. Anisotropy is something that many AM technologies has to deal with. That is direction-dependent properties, which should be considered when we design and specify the part. Let's look at some of the typical validation methods for the internal structure. For metals, the microstructure can be validated by use of conventional metallographic methods. That means that a part of the material is embedded into a resin, and then the surface is polished smooth with a grinding and polishing machine, and after that be examined by use of microscopes. Porosity and overall density can be validated by use of non-destructive methods. This could be a CT scan where the part is fixed and then X-rays passes through in order to visualize dimensional deviations or internal defects. This can be done on the entire part or at a specific region of interest. The achieved data can then be compared with the associated CAD model. Also, a pore analysis can be done with CT scan to determine size, number, shape and location of pores in order to determine their impact on the functionality of the component. Another common option is the Archimedes principle, where a material sample is weighted on a high precision balance as well as in liquid medium, and then the difference between the two weighting result is calculated. This method can be used as a precise, fast and also simple method to determine the material density. If we look at mechanical properties, deviation of mechanical properties is often related to internal errors like porosities. It could also be machine deviations or non-optimized process parameters or improper heat treatment. When dealing with the mechanical properties, the typical validation methods are the same as for conventional manufacturing processes. That include tensile testing, fatigue testing, Sharpie impact testing, and hardness testing. Finally, let's take a look at some of the standardization activities within additive manufacturing. When we talk about quality control, an important aspect to mention is also standardization. So why do we need standardization for additive manufacturing? It is to get a common understanding of terminologies, the many different processes, materials and test methods, and also quality specifications and delivery conditions. Various organizations and industries are contributing and collaborating. A collaboration agreement between ASTM and ISO was established back in 2011, jointly to develop international standards and avoid duplications. If we look at the AM standard structure, it can be divided into general standards, category standards, and specialized AM standards. General standards are specifying general concepts, common requirements, and can be used to most types of AM materials, processes, and applications. Category standards specifies requirements that are specific to a material or a process category. Finally, specialized AM standards specify requirements that are specific to a material, process, or an application. Here we see 5 examples of process material specific standards for laser powder bed fusion in metal. These standards are used to define material classes, which means mechanical properties, test methods, acceptance criteria, specifically for powder bed fusion in metals. It is important to note that not all AM processes has the same number of standards available. It usually depends on how industrialized the process is. Another example is a standard that is specific to critical components. This standard is, for instance, used in the aerospace industry and medical industry. The standard defines how the AM production can be controlled and also how machines and processes continuously can be monitored. This final example of a standard covers test method versus application. This standard considers where and how the product should be used. Is it a prototype, or is it an engineered component, or is it a critical component with risk for personal safety? The standard defines 3 risk levels with associated test categories and test methods. You can see the risk levels in the table to the right. That brings us to the end of this video. Thank you for watching.